In this section, we will demonstrate how Neven's congruence can be adapted to address primes of the form 8k plus 1 through a twin infinite descent procedure. Notice that the form is 8k plus 1, so k may be even or odd. This can be concisely expressed as k equals 2 raised to r times s, where r is equal or bigger than 0 and s is odd. The key here is modifying the procedure according to r. We'll start slow, first examining where r equals 0, then progressing to r equal 1, and so forth. Ultimately, we will synthesize our findings to illuminate the principles governing the general case. When r is 0, k is odd, and so k plus 1 equals 2 raised to w times z, where w is equal or bigger than 1. When n is a quadratic residue of p, then n raised to p minus 1 over 2 minus 1 is divisible by p. Since 8 divides p minus 1, then n raised to p minus 1 over 2 minus 1 can be factored into those two brackets, with p dividing one of them. In the first case, n raised to p minus 1 over 4 minus 1 is considered. The next step involves multiplying all terms by n raised to 2 raised to r plus 1. Since r equals 0 in this case, we obtain n squared. After substituting p with 8k plus 1 and simplifying, the left side of the equation becomes n raised to 2 times k plus 1 minus n squared. Next step is substituting k plus 1 with 2 raised to w times z. Since w is bigger or equal to 1, then w minus 1 is at least 0. So we can factor 4 from 2 times k plus 1. To identify the smallest fourth power minus a square divisible by p, we evaluate this congruence, thereby determining m. Subsequently, we factor the difference between a fourth power and a square as m squared plus n times m squared minus n. Therefore, p divides one of these factors. If p divides m squared plus n, our objective is achieved. Conversely, if p divides m squared minus n, we then seek a value, u, that is a quadratic non-residue of p. In other words, p divides u raised to p minus 1 over 2 plus 1. Combining these two congruences yields a square plus n divisible by p. The remaining task is to determine the smallest value of that square, denoted as v, the residue of the congruence m times u raised to p minus 1 over 4 modulus p. Ultimately, this leads us to the desired equation, v squared plus n equals p times k sub 4. We should now focus on the scenario when p divides n raised to p minus 1 over 4 plus 1. We just need to repeat the procedure done before, only that we would end up finding that p divides m raised to 4 plus n squared. To tackle this, we utilize u again, a quadratic non-residue of p. By combining both congruences, we establish that the difference between a fourth power and n squared is divisible by p. The next step entails identifying the smallest fourth power that satisfies this divisibility, denoted as the residue, x, of the congruence m times u raised to p minus 1 over 8 modulus p. Therefore, we can now factor x raised to 4 minus n squared as x squared minus n times x squared plus n. Consequently, we find ourselves in a situation akin to when factoring m raised to 4 minus n squared. should p divide x squared plus n, our task is complete. However, if p divides x squared minus n, we simply replicate the steps done for m squared minus n. Let's now examine prime 41, an example when r equals 0. Since 2 is a quadratic residue of 41, then 2 raised to 41 minus 1 over 2 minus 1 is divisible by 41. This leads to 41 dividing one of the two brackets. If 41 divides the plus 1 bracket, then we proceed by multiplying all terms by 2 raised to r plus 1, where r equals 0, thus multiplying by 2 squared. Substituting p with 8 times 5 plus 1 simplifies the exponent to 2 times 5 plus 1. Given that 5 plus 1 equals 2 times 3, we reach a fourth power plus a square that 41 can divide. As 2 cubed is smaller than 41, that's the smallest number we can find. The next step involves finding a quadratic non-residue of 41, with 3 being the smallest one. Consequently, 41 divides 3 raised to 41 minus 1 over 2 plus 1. Combining both congruencies yields that the fourth power of 8 times 3 raised to 5 is congruent to 2 squared modulus 41. The residue of the congruence 8 times 3 raised to 5 modulus 41 is 17. Hence, 41 divides 17 raised to 4 minus 2 squared. Consequently, when factored, 41 divides either 17 squared minus 2 or 17 squared plus 2, with the former being true. The subsequent step comprises applying the congruence involving 3 as a quadratic non-residue of 41. Combining both congruencies reveals that a square plus 2 is divisible by 41. Finally, finding that minus 11 is the residue of the congruence 17 times 3 raised to 10 modulus 41, we conclude that 11 squared plus 2 is divisible by 41. In other words, 11 squared plus 2 equals 41 times 3, the solution we were looking for. We say that this is a twin infinite descent method. Let us explain why. There's a first infinite descent that encompasses all these congruencies that we've deduced during the procedure. That's the first infinite descent with their corresponding equations. And then there's a second infinite descent, the simple descent procedure tailored for finding representations of primes as x squared plus minus n times y squared. Now, let's examine the case r equals 1, that is, when p is of a form 16k plus 1. Continuing with the same methodology as previously employed, we multiply by n raised to 4, ultimately yielding an 8th power minus a 4th power divisible by p. If p divides m squared plus n, then we are done. If instead p divides m squared minus n, we integrate this with a congruence involving a quadratic non-residue of p, leading to a v squared plus n divisible by p. When p divides m raised to 4 plus n squared, then we can also apply a congruence involving a quadratic non-residue of p, thus finding a 4th power minus a square divisible by p. Consequently, we either obtain a x squared plus n divisible by p as intended, or if x squared minus n is the case, then we apply a congruence involving a quadratic non-residue of p as shown before. If instead p divides n raised to p minus 1 over 4 plus 1, then applying the same methodology yields an 8th power plus a 4th power divisible by p. Subsequently, by combining this result with a congruence involving a quadratic non-residue, we achieve an eighth power minus a fourth power divisible by p, and then apply the needed steps in order to find a square plus n divisible by p. Let's now examine prime 113, an example with r equals 1. In this instance, 113 can be expressed as 8 times 14 plus 1, signifying r as 1 and s as 7. Consequently, s plus 1 equals 2 cubed. Initially, we find that 2 is a quadratic residue of 113. Upon factoring this expression, we discover that 113 divides 2 raised to 113 minus 1 over 4 minus 1. Subsequently, we multiply all terms by 2 raised to 4, adhering to the condition r equals 1. We then substitute p with 8 times 14 plus 1 and simplify, leading to the identification of an expression in the form 8th power minus 4th power, which is divisible by 113. This expression can be factored as 16 squared minus 2 times 16 squared plus 2 times 16 raised to 4 plus 2 squared. A straightforward examination confirms that 113 divides the third bracket. Moving forward, we determine that 3 is a quadratic non-residue of 113, implying that minus 1 is the residue of the congruence involving the fourth power of 3 raised to 14 modulo 113. By combining both congruences, we establish that 113 divides 51 raised to 4 minus 2 squared, consequently leading to the divisibility of either 51 squared minus 2 or 51 squared plus 2. The first case is true. 51 squared minus 2 equals 113 times 23. And the final step, we apply once again the congruence involving 3 as a quadratic non-residue of 113. Following the same methodology as before, we arrive at the desired solution. 26 squared plus 2 equals 113 times 6. Once finished, we can identify the congruences of the first infinite descent. From the equations derived in the initial infinite descent, we proceed with a simple descent method to determine the representation of 113 in the form of x squared plus minus 2 times y squared. Well, now it's time to examine the general case for primes 8k plus 1. When n is a quadratic residue of p, then n raised to p minus 1 over 2 is congruent to 1 modulus p. Consequently, p divides either n raised to p minus 1 over 4 plus 1 or minus 1. We proceed by multiplying both sides of the congruence by n raised to 2 raised to r plus 1. Then replacing p and simplifying. It's worth remembering that r is equal to or greater than 0. Thus, 4 divides 2 raised to r plus 3. Also, notice that s plus 1 equals 2 raised to w times z. By combining and simplifying, the power of n becomes 2 raised to r plus 1 times 2 raised to w times z. Since w is equal to or bigger than 1, we can restate the left side as n raised to 2 raised to w minus 1 times z, all raised to 2 raised to r plus 2. Next, we compute m, the residue of the congruence of n raised to 2 raised to w minus 1 times z modulus p. Thus, p divides either m raised to 2 raised to r plus 2 plus minus n raised to 2 raised to r plus 1. When dealing with a difference, we proceed with factorization and check whether p divides m raised to 2 raised to r plus 1 plus minus n raised to 2 raised to r. In such instances, we can continue factoring until we attain the desired solution or encounter a sum of powers, where the first power is double the second. When dealing with our sum of powers, it is necessary to find a quadratic non-residue of P. This allows for the combination of both congruencies to resolve a difference of powers, thereby enabling factoring. Notice that we'll end up arriving at the difference of a 2 raised to r plus 2 power and a 2 raised to r plus 1 power. As long as we reach that difference, we can proceed with factorization and check if P divides one of both brackets until we reach a square plus n that P can divide. It's time to see an example of the procedure. As 353 equals 8 times 2 squared times 11 plus 1, we set the values of r as 2, s as 11, and w as 2. 167 is a quadratic residue of 353. Also, 3 is a quadratic non-residue of 353. Given that we've established that P divides this congruence highlighted in light blue, we must now apply it using the specific values relevant to this case. Let's briefly outline the subsequent steps required. In the first step, we deduce that 353 divides 8 raised to 16 plus 167 raised to 8. In the second step, we combine the result of a first step and the congruence that involved 3 as a quadratic non-residue. And so we find that 353 divides 234 raised to 16 minus 167 raised to 8. As we can factor this difference, we check that 353 divides 234 raised to 8 plus 167 raised to 4. In the third step, we repeat the procedure, combining the outcome of the second step with a congruence involving 3 as a quadratic non-residue. Consequently, we determine that 353 divides 183 raised to 4 plus 167 squared. In the fourth step, we apply the procedure once more, resulting in 353 dividing 251 squared minus 167. In the fifth step, we employ the same procedure one last time, yielding that 353 divides 48 squared plus 167. Indeed, these 5 steps constitute the first infinite descent. The equations derived from these steps serve as the foundational elements required to kickstart the second infinite descent, which occur as we apply the simple descent method. Finally, let's examine an extreme case, one that involves Fermat primes. 11 is a quadratic residue of 257, and 3 is a quadratic non-residue of 257. Starting with the congruence derived and highlighted in light blue, when applied to the present case, it reveals that a 127th power minus a 64th power is divisible by 257. Upon applying the first and second steps, we deduce that 257 divides 11 raised to 64 plus 11 raised to 32. Given that congruence, and combined with a congruence involving 3 as a quadratic non-residue, we end up finding that 257 divides 99 raised to 32 plus 11 raised to 16. Applying this outcome and the congruence involving 3 as a quadratic non-residue, we conclude that 257 divides 52 raised to 16 plus 11 raised to 8. Repeating this process, in the fifth step, we find that 124 raised to 8 plus 11 raised to 4 is divisible by 257. The sixth step is much the same, yielding 36 raised to 4 minus 11 squared is divisible by 257. Upon factoring, we verify that 257 divides 36 squared minus 11. Finally, in the 8th step, we apply the same combination of congruences, leading to the desired solution. 257 divides 62 squared plus 11. To recap, these congruences form the basis of the first infinite descent. Applying the simple descent method introduces a second infinite descent. In summary, this section extends Neven's congruence procedure for primes of the form 8k plus 1, effectively establishing a twin infinite descent protocol for determining whether such primes can be represented as x squared plus minus n times y squared. The initial infinite descent involves adapting Neven's congruence for primes of this form to determine the modular square root. Subsequently, the second infinite descent employs the simple descent method to find out whether the primes possess the desired representations for a given n. Remarkably, the most extreme cases for this twin infinite descent protocol are Fermat primes. In the next subsection, we will analyze Tonelli's-Shank algorithm, derive a corresponding formula, and compare it with the twin infinite descent protocol developed in this subsection.